Now we have Gili. Gili is a fourth-year computer science PhD student, co-advised by Professor David Parkes at Harvard and Professor John Horton at MIT. Gili is interested in questions surrounding how modern AI can be leveraged to enable practical implementations of search and matching mechanisms. Her work is supported by Upwork. So let's welcome Gili.
Thank you so much for having me today and coming out to the talk. So today I'll be talking about AI agents and how they may be able to facilitate preference elicitation and enable sophisticated market designs. This is joint work with Ben Manning and John Horton at MIT. So some motivation. It goes without saying that generative AI is changing every facet of our lives. This conference would not be present without it. And one of those things that is changing is our labor markets. In this paper, what we're trying to ask is, can AI agents understand people's preferences well enough to do a good job matching workers to jobs? So we ask around this, we build this up through two research questions. First, can LLMs infer people's rankings over jobs from their own stated preferences? And second, how do LLM-based rankings change the outcomes that markets produce at scale? So we'll start with the first question. And the way we sought to understand this question is by designing an experiment. So we designed a simulated prolific task market, and we recruited participants to fill out a custom survey about their preferences over tasks. We ran this in a two-stage study. I'll get into the details in a second, but we had basically 500 people complete the first part of our survey, and then we invited those exact participants back, and 364 came back for the second part of the validation part of our survey. And as I mentioned, they filled out a custom survey on their preferences over prolific tasks, and this is particularly apt because this is something they do for money. This is something they do for a job, so they have particular tastes. And we offered them an incentive so that they'd give honest and accurate preferences. And so we offered them the incentive of a tailored task depending on how they filled out the survey today. Okay, so the experiment ran in two stages. First, there was a preference data collection phase. Then we had an offline LLM ranking generation. And finally, we had a stage at the end where we went back to the same participants to evaluate the performance. So the first stage, what did we collect? What did we have people tell us about their preferences? We asked two pretty simple questions. The first thing we asked is simply put, state your preferences in paragraph form. Assume you're describing your tastes over prolific tasks to a friend who's choosing tasks on your behalf. How would you do this? What should they avoid? What should they favor, etc.? And then we asked them to do a second exercise, which was a ranking exercise. So we showed them a bunch of representative prolific tasks, and we asked them to re-rank. We showed them the tasks in random order. We asked them to re-rank these tasks to their desired preferences, from most preferred to least preferred. And we had three treatment groups. A third of the participants, we showed them 10 tasks that they needed to drag and drop to their preferred tastes. A third of the participants ranked 25 tasks, and a third even ranked 50. And you'll see why these number of tasks are so large a little later. But the tasks were presented in random order. And basically, they had to click to re-rank the tasks. And we could also measure them doing some research about the given task. So we have this view detailed button that we track in our survey when they clicked it, because this allows them to learn more information about the given task. For example, the pay, the description, not just what the task name is. And as I mentioned before, we made this incentive compatible by telling them that we would use these paragraphs and these rankings to tailor a bonus task that they particularly like, perhaps a high-paying one. So how did our participants respond? Okay, so first off, they gave us very detailed responses. So this participant wanted shorter tasks, whereas this participant really prioritized doing tasks on their phone. And they showed us very diverse results as well. But the key point that unified these is that participants convey a lot of information about themselves through natural language text. And this could even be thought of as a sort of behavioral program. As a small preview, we're going to eventually provide these paragraphs to LLM agents as context, and then have the LLM agent do a bunch of ranking for us as well. But we'll get to that in a minute. First, let's understand what people are doing in the second part of our experiment, where we ask them to re-rank a bunch of tasks. So this schematic shows for one single person. On the x-axis, I show the rankings. This person was in the m=50 treatment group. They had to re-rank 50 tasks. And along the x-axis is their move number. So we have these little dots. They represent the randomized start order of the tasks. And the arrows represent how the participants moved. So this participant's first move was to take the 49th ranked item in the randomized ordering and put that one first. Maybe they really liked it. Maybe it paid really high. And this is a full schematic of how this particular individual ranked. And so I don't know if you've ever tried ranking 50 options in one sitting, but it's maybe not the easiest task. And what we noticed in our rankings is that people are not conveying their full preferences, especially as the choice set grows. There's cognitive load constraints, there's time constraints. This is, after all, only a survey, et cetera. So the question we ask is, can LLMs help? So now we get into the second part of our experiment, where we describe how we used an LLM to generate a ranking. So basically, we did something pretty simple. We took, for each person, we took all m of the tasks that they individually ranked, the ones they saw in part 2 of phase 1, and we took their paragraph taste preferences. I prefer tasks that are shorter with a mobile phone. Then we gave the LLM the following prompt. Given the following preferences, which of these two tasks do you prefer? With the description and the pay, et cetera. And we repeated this for all m_2, for all different pairs that you could possibly get from combining two options in their original menu set. And finally, we fit a Bradley-Terry model. Basically what this means is it's a statistical model that takes pairwise preferences and turns them into a ranking. So now what we have is for each person, we have their human ranking from question 2, and we have this LLM-generated ranking that was made out of a single taste paragraph. Okay, so now we want to evaluate how do these two objects compare. But in order to do this, we need to establish some sort of ground truth. And we've already agreed that the humans in phase 1 didn't rank those M tasks fully. So in order to give a better measure for the ground truth, we had a phase 2 where we went back to the exact same participants and asked them again. Now, over a pair of tasks, this is an easier task, which do you prefer? So before we were assuming they can't do a great job on m=50, but we here do make the strong assumption that on m=2, when they only look at 2 things, they can do a good job. And we did this 5 times for each person with 1 attention check. And how did we evaluate it? Basically what we did is I'll go through a simple example. If the human ranking ranked A, B, C, and the LLM ranked C, B, A, suppose that in the ground truth in the second phase, this same participant who reported A, B, C, and C, B, A chose option A over option C, then this would mean the human ranking was correct because it ranked A over C, but the LLM ranking was not correct in this case. So this is how we measured success. So now the question is, how do human rankings compare to LLM rankings? On this graph, we show accuracy on the y-axis, and again, number of tasks on the x-axis. So these are our 3 different treatment groups. And what we see is that when the number of options to rank, when m equals 10, is small, or relatively small at least, human accuracy outperforms LLM accuracy, although those error bars are quite large, but let's say that it outperforms. And however, what happens is that as the number of tasks, as the choice set increases, the human performance degrades. What does the LLM ranking performance do? Well, the LLM ranking performance remains fairly consistent because all it's doing is just taking these random pairs and asking the LLM, which do you prefer? It's doing the same process over and over again. And so while maybe in the m equals 10 scenario, the human beats the LLM, as we get more and more options to rank, the LLM performance remains consistent. Although 65%, we might be able to do a little better. But tastes are very messy. So what do we see? We see that LLM rankings show stable accuracy even as menu size grows, and low marginal human ranking effort for an additional task. Whereas the human ranking shows declining accuracy and rising effort cost. If I have an additional task I need to go out and now rank, if I'm a human, I have to do a bunch of comparisons. But the AI, I've already paid the sunk cost of writing my taste paragraph, so the AI can do this to me at nearly 0 marginal human cost. So what can we do with this? And in this is where we get to the second research question, and I'll give a preview. This is ongoing work, but the question we want to ask is, how do LLM-based rankings change the market outcomes? So in order to understand this, we designed, with these same rankings, we designed one-to-one matching markets with both the LLM-based rankings and the human-based rankings. So the way we constructed the market was, for each participant, we entered them into 2 markets, with each of these markets containing m people. So if I was in the treatment group that ranked 10, I'd be put into 2 10-person markets. We made one of them congested and one of them uncongested. So every participant in the market is someone in our original phase 1 surveys, one of the 500 people, and we just split them up into 10-person markets, or the people who ranked 25 options were in 25-person markets, etc. So basically, each person was in 2 markets that had m people, each of whom ranked m choices. And for each market, we ran the same one-to-one matching mechanism twice. So first, we ran a random serial dictatorship, which is an algorithm for matching rank preferences to options. And we did this once based on the human rankings. And then in run B, we used a random serial dictatorship to assign the workers to jobs based on the LLM rankings. So now we have, for each market, we have 2 options. We have 2 matches, one based on human, one based on LLM rankings. And so now we do the same thing as before. We collect ground truth by showing 2 pairwise questions. Do you prefer this or this? Do you prefer this or this? Right? The human doesn't know anything. It doesn't know they were even in markets. They're just stating their preferences. But under the hood, we know that question 1 came from the congested markets. Question 2 came from the uncongested markets. Match A came from the human-derived preferences. Match B came from the LLM-derived preferences. And so we asked these two questions. So how did our participants respond? So what we measured here is basically, again, a very simple success metric. Did people prefer the match that the LLM ranking would have matched them with over the match that that their own human rankings would have matched them with? And I should reiterate, like, every person in the market uses the human accuracy, and every person in the market uses the LLM accuracy for the two matches. And so on the x-axis, I show this probability that the LLM beats the human match. And on the y-axis, I show the number, on the x-axis, I show the number of tasks, the 3 different treatment groups. Oops. So how did we do? We did all right, let's say. I think the strongest thing we can say from our current results is that LLM-based matches are approximately acceptable to human-based matches. But remember, they come at a lower cost, so we also have the cost factor. And we see that AI rankings become more useful as markets become more congested. The orange line shows our congested market treatment, and the green line shows the least congested. We see in most of the experiments that the more congested markets see more benefits from using the AI rankings. This might be because humans maybe can rank all their top first preference, but what if I'm in a market and everyone ranks the same top preference as me? Then someone's gonna be unhappy. And so the idea is using LLM preferences, we could get a more nuanced understanding of people's maybe lower tiered, lower ranked options. So some conclusions in future work. Basically, what we've seen so far is that results indicate that LLMs might be effective tools at eliciting preferences. And the next step is basically expanding on the second part of the paper that I mentioned and asking which market mechanisms can now we make feasible using these LLM-generated rankings at a lower elicitation cost. So thank you very much. Thanks for having me, and I'd be happy to take questions.
Right, so let's take a few questions for perhaps 5 minutes. Great talk, really enjoyed it. Do you worry about agents maybe misreporting their preference, especially if certain jobs are more appealing than others?
Yeah, so I guess the question was, do I worry that agents are misreporting preferences because some jobs might be more appealing than others? I guess the first clarifying question I would have is, do you mean the AI agents or the human agents? Yeah, so the human agents will probably try to strategize in a way that they normally try to strategize. And we're assuming here that the AI is not a platform's AI. Each agent has their own AI working for them, so it is tuned to the best of their incentives. So you could imagine a world where the platform owns each of these AIs, and then you might run into more trouble, because then there might be mixed incentives that the platform wants to maximize matches instead of getting me specifically a specific task.
So the difference between the performance of the human and the LLM comes from, or I am guessing, that maybe it's because fatigue, like you don't, as a human, you cannot rank 50 different alternatives. But could it also be that the LLM is able, based on the description that the human is providing, kind of trying to formalize something in a more consistent way as the human, and therefore when ranking things is more accurate all the time? So I was just wondering, is it more that the LLM can do better, or the human is not very good?
Yeah, so the question was, is the results I'm showing more a function of the human getting bad or a function of the LLM remaining consistent? I think it's some of both, right? So the human fatigue problem is definitely an issue, and sort of what we're trying to show, in fact, is that it becomes super costly to do a bunch of these rankings. So we can't get the nuanced enough data to run something like even a random serial dictatorship in practice, because we don't have 1,000 job rankings for each person. And I think the other part is that the LLM doesn't have this fatigue. So hypothetically, statistically speaking, if I take 2 random jobs today and 2 random jobs tomorrow, it should do a consistent job on these 2 questions. Maybe it won't, but yeah.